Okay, we'll go ahead and get started here on this next session. We've got two presentations in this session with two different perspectives on sensor evaluations. The first will come from Brandon Feenstra with South Coast AQMD, and the second with Koki Shimahashi with CARB. So please welcome Brandon.
Thank you, Kyle. And again, my name is Brandon Feenstra from South Coast AQMD. And I've been working with the AQ-Spec group for about 4 years since it was started in 2014. And I'll talk to you about some of the sensor evaluations that we've been doing. First, talk about the background leading up to AQ-Spec. Talk about field and laboratory evaluations that are performed within the sensor evaluation program. And highlight some of the field PM sensor results that we have for 12 sensors that is in a paper that's under review. So we all know about the historical ambient air monitoring with the Clean Air Act and the approved reference monitors, and that building out those regional networks to determine the attainment of the national ambient air quality standards. Recently, there's been the legislation for AB 617. Many of us are aware of that, mandating the community monitoring, bringing that scale down from that regional attainment, and doing those measurements now at a more local, neighborhood, community type level. And as well, there's an introduced bill, it's not been passed, but a House Bill 1284 called the Crowdsourcing of Environmental Data Act of 2019. And that's an amendment to the Clean Air Act, and to allow states to use sensors to supplement their current monitoring networks and to determine whether an exceedance has occurred. And so that's an interesting legislation piece that's been introduced. It has not been passed, but just to give you an idea of what's being put out there for what sensors can do. And we'll look at some data which will give us some insights into whether or not that's a good idea later. Low-cost sensors, these are not new. They've been used for many years. We know about the coal mines, canaries in the coal mine, and some of this has been increasing in the last years with technology advancement, both on the Internet of Things revolution and as well on some of the hardware costs for these low-cost sensors. And we see that in 2011 with the release of the Geiger counter for the Fukushima disaster in Japan, where community scientists were doing monitoring around that disaster and collecting that data in real time and putting it on maps. And then in 2012, the Air Quality Act came out, and EPA then recognized this movement. In 2013 was starting the first Next Generation Air Sensors Conference. South Coast responded to this emerging marketplace of low-cost sensors in 2014 with the creation of AQ-Spec. Since then, last couple years, there's been a significant increase in startups that are selling sensors on the market, ranging from $150 all the way up to $3,000. And if you look at the literature, there's been a lot of literature with people and researchers developing networks of sensors, increasing that spatial temporal resolution. And some of the potential applications for these sensors are fence line, community, hotspot, personal exposure, and science education. So where can these sensors fit in and to what we currently do with the public health perspective? They can tell us what are the concentrations at a more spatial and temporal resolution by developing out those dense networks spatially. And they can also inform some of the mitigation efforts and be able to determine what are the sources, the relative contributions, and determine whether air pollution is being transported into a community or whether it's being locally produced. And it's also able to inform and empower the public, and being able to collect data in a local environment that is applicable to somebody's personal exposure, and then they're able to modify their habits based on the data collected at their home, at their workplace, or while they're out and about and mobile. So AQ-Spec was established in 2014 by South Coast AQMD. The main goals were to provide clarity to this emerging marketplace, provide all the information of our evaluation reports online, so different air quality districts, researchers could go online, take a look at what the evaluation results are, and kind of make a small list if they wanted to develop a sensor network. Minimize confusion by having an independent evaluation program, And there's the criteria for sensor selection. So we're looking for devices that are commercially available, devices that measure in real time with less than 5-minute time resolution, a device that is sensitive at ambient levels as well, and that we can deploy for 2 months in the field and retrieve the data. That sometimes can be a significant challenge of just receiving data from these devices. When we get these devices, we test them in the field at our Rubidoux air monitoring station. This is an inland site. It's fully instrumented for the criteria pollutants and several of the toxics. And sensors are tested in triplicate, and they're tested for 2 months. And during that time, we collect the data, we time match it to the reference instrumentation, and then we run regression statistics, provide that evaluation report on our website. All those results are publicly available on our website. The chamber, if the devices perform well in the field, they will then be taken to our laboratory. And in the laboratory, we kind of have 2 different setups here. On your left-hand side, you'll see the setup for our aerosol testing, right-hand side for gas testing. By using the drum, it reduces our volume by about 1/3, so we're able to use less gases when we're actually using cylinders to test our gas. And it has a full HVAC system, so we're able to control for temperature, relative humidity, and vary those, cycle those, as well vary and cycle our pollutants of concern, whether it's aerosols or whether it's gases. So just some history of our laboratory evaluations. We received the chamber in the summer of 2015, and AQ-Spec staff worked with the developer and to customize the system to meet our requirements that we had foresaw at that time, and also develop methods for aerosol and gas phase testing. And that took about 6 months and 12 months with working with the manufacturer. So a lot of work went into developing that. Results can be found in an article written in Atmospheric Environment and on the development of an environmental chamber for evaluating the performance of low-cost sensors. So the result of that is we have a state-of-the-art system. It's able to systematically evaluate the performance of sensors, able to produce stable and reproducible aerosol and gas test environments, and then also do that on a range of relative humidity, temperature, and target pollutant and interferent pollutant. So if we're testing for ozone sensors, we can also test that sensor for interfering pollutants. And when the system is also set up for several different data communication options for sensors. So there's a list of the evaluation parameters. Currently, there's 16 laboratory evaluations that are available. They are online. There's the website. Feel free to go there and find our evaluations. All that information is open to the public. Some of the challenges that have encountered through developing the protocol and developing the system is the stability of large particle environments. It's the PM10. And part of that's due to the nature of those test particles. Also, sensor degradation performance experience is difficult doing that long-term test, and temperature and RH cycling tests for long periods of time. So on the horizon, South Coast AQMD and the AQ-Spec program is currently developing a ASTM testing protocol for low-cost air quality sensors, also a VOC sensor testing protocol, and we're under development on getting a contract in place for a second chamber system to be delivered at the end of this year, so a larger chamber system that would be able to accommodate more than 3 sensors. So this would ideally hold about 20 sensors, can be used for calibrations, aging, vibration, wind effects. So it's going to have a lot more features than our current chamber system. And the primary use of this is going to be using in our AQ-Spec sensor library system, as well as developing testing protocols for conducting mobile ambient air monitoring sensor evaluations, and for the development of sensor performance standards. So currently, right now, we are an evaluation program, and so kind of moving towards that kind of developing performance standard for sensors, looking on the horizon for that. So kind of switch gears here. I'm going to jump back into field testing. This is a paper that's in review, and it has reviews 12 low-cost particulate matter sensors measuring PM2.5. We'll look at a couple different performance evaluation parameters. And we've taken all of these results, AQ-Spec results from these 12 sensors, a couple things to improve the inter- and intra-model variability between these. Any concentrations of PM 2.5 that are greater than 50 micrograms per cubic meter were removed. And as well, if there was any missing data from one of the 3 sensors or the BAM, we had a BAM 1020 for PM 2.5 is missing, that would be removed from the analysis. So 12 sensors, again, this is a lot on this slide. Time resolutions varied from 1 minute to 5 minutes. The price range varies as well from $150 to about $3,000. And just kind of another background, looking at some of the statistics I'm going to show in the next couple of slides. I'm going to talk about bias and measurement errors. So bias error is going to be the sensor minus the reference, which would be the BAM. This is on an hour divided by the number of data points. So that's giving you, if it's a positive number, the sensor is going to overestimate typically. If it's negative, it's going to typically underestimate the reference concentration. The mean absolute error is the same calculation, just the absolute value. So it gives you an indication of the total measurement error of that low-cost sensor. So jumping into some of these results, this is also a large paper plot with a lot of data. We'll look at it one by one, or just to get some of the highlights. So we'll start off on the top with that yellow for the AirQual AQY. You can see it has a decent R-square, greater than 0.75, slope is close to 1, has an intercept offset, and that offset is very close to what our mean bias error is. So that's something that could be corrected potentially with a 0 offset or correcting for that intercept. We move on to these 3 sensors. We'll kind of group them together in the blue. These 3 sensors tend to overestimate the BAM concentrations. Some of them have good R-squares, 0.9, some of these at 0.5, 0.7. But if you look down on the slope column, which is going to be right here, you can see some of these have a slope of 2, so heavily overestimate PM 2.5 concentrations on a 2-month evaluation at our Rubidoux air monitoring station. You will notice, though, that the bias errors are high. These ones in the 17s, 5s, 3s. Those are typically a good portion of the absolute error. So you would be able to potentially get rid of that bias error by doing some ordinary least squares regression calibrations, and you could get a large percentage of that bias out, but you would still have some measurement error still. This one here, the Kytera laser egg, is a good example of why R-square is important. So if we look at slope, it looks great at the 1. Intercept is looking good, close to 0. However, R-square is kind of low, and you can see that with the proportion of bias error to absolute error. There's a real low portion of bias error to absolute error, so it's very random error for this sensor. So it overestimates and underestimates randomly. And lastly, we'll take a look at the Yoo-Hoo, which has R-square of 0, slope offsets 0. So just an indication of a wide range of performance with low-cost sensors. And some of these cost very similar. So like a Yoo-Hoo may cost very similar to 3 or 4 other on this list. So performance is not directly correlated with cost. So looking at the relative humidity and bias error, what I'm showing here is bias error. So this is whether it is positively overestimates the reference or negatively overestimates the reference. And then the x-axis is relative humidity. So trying to figure out where our errors are based on relative humidity. And some of the interesting things to notice here, just to note, the BAM is equipped with the heater. The low-cost sensors measure air at whatever the ambient concentrations are and ambient RH. Some of the sensors do correct for relative humidity for their PM 2.5 measurements. And you can see that on the top portion here, where these sensors here have kind of a flat line for error as RH increases. So those ones correct. And as you kind of come down the plot here, you start seeing sensors that are impacted more by that RH. So as RH increases, we're seeing that measurement error also increase. So you can get some different things going on in coastal environments when you have these deployed out. A very similar plot here is the same on the y-axis is going to be the bias error. The x-axis has been changed to the BAM, PM 2.5 hourly concentrations. And the idea here is trying to figure out when the bias error changes based on PM 2.5 concentrations. So just to take a look at a couple for example here, we can see that it's like a systematic error here, and then it turns into more of a random error as you get above this 20, 25 micrograms per cubic meter. So you may be able to correct for some of this at the lower concentrations, but at higher concentrations, you're going to get that random error that will be more difficult to correct for. And then if you look here at the purple air sensor, you can see that it has a lot of random error where it overestimates, underestimates fairly evenly between 0 and about 15 micrograms per cubic meter. And then above that concentration, you see that more systematic overestimation of PM2.5 that you may be able to correct out. So looking at this with an idea of how can we correct this data and maybe applying machine learning with having relative humidity, the BAM concentration information. Some of this random error is going to be very difficult to deal with. The more systematic will be easier to deal with. Some of them, like the Yoo-hoo here, these ones a little bit harder to get a feel for. You can see that this strongly overestimates PM2.5 concentrations. So with that, we'd like to thank you. It's a whole team at South Coast AQMD that works on this, not just myself. And here's the list. If you go to our website, aqmd.gov/AQ-Spec, you can find a contact us information, and you can reach out to us both by phone number and an email address.
All right, we'll do questions at the end, everybody. Okay. Next up, please welcome Koki.
Thanks, Kyle. I'm Koki Shimahashi from California Air Resources Board. I'm going to talk about our sensor performance evaluation program. And this is outlined today. I'm going to start with background and motivation, why conduct sensor evaluation, and our role, and followed by some performance evaluation application examples, and ongoing and future work at the developing resource tools and summaries. So let's start with background. So speaking of low-cost sensors, they're very popular right now because they are very reasonable, inexpensive, and they're available in the market. And then if I look at the numbers, it's about 1,600 operational purpose sensors, which is a PM sensor with $200 in California in 2018. And then they are available to community and community members, citizen science. There's lots of information on the website how to build sensor air quality stations, monitoring stations. So talking about the community air grants, if I look into it, there's 24 out of 28 grants. You use local sensors, and then about 350 PM sensors going to be used. And here's another example on right-hand side. There's an article from website. They like to install some local sensors to track the air quality in Mexicali. So these are good example of the increasing awareness of the local air quality and the use of local sensors. Let's move on. So we talked about sensor evaluation, but unlike the regulatory monitoring station, those sensors doesn't come with nice calibration or audit processes. So understanding the performance is a very key to interpreting data. And let me just quickly talk about some performances as example. This chart is from the EPA's sensor guidebook. Like accuracy is like how close to the true value. Like precision is like how consistently hit the same value. I would have to say noise. And bias is a systematic error. And if that converted into time series data, this is a chart from EPA's sensor book. And this is ozone PPB data. The red ones is, how to use this one? Oh, here you go. The 1 minute measurement. And then green line is a 15 minutes average measurement. But the red one, those zigzag, I would have to say it's because of precision or noise. So I don't really, if I want to track the systematic trend, I wouldn't really look into this red zigzag line. So this is a kind of example of understanding performance. And this is important to know interpreting the sensor measurement. And let's move on. Let me talk a bit about California Air Resources Board roles. Our role is to support CARBs and communities monitoring programs, like the Brandon mentioned in the previous presentation. We can select those sensors, and then we first do co-location with reference monitoring station. That's a good way to, from out of the box, understand the out of the box sensor performance. And then in addition to that, we like to dive into the data and then come up with some models, algorithm, so that it can be used to different places all over the California. So identify the appropriate application is one of the things. And also we're working on sensor network, because sensor can, unlike the regulatory monitoring stations, we have lots of sensors, well, monitoring stations. So the network quality is something we are working on. And lastly, I like to make information available via AB 617 Resource Center or conference like this. So again, the message here is promoting a best practice and share information. So now, let's move on to sensor co-location. This is a picture photo of our monitoring station. We do have FEM instrument, and we have different kinds of local sensors. But because of the time limit, I'm basically focusing on the appropriate data for this conference. And let's move on. And once you collect the data, like I mentioned, we're going to dive into the data analysis. But before jumping into this chart, let me just explain a little bit about low-cost PM sensors. Low-cost PM sensor usually uses the optical particle counter. And then what it does is it gets using a light scatter signal, and then that is converted into a particle count and size, and then with some assumption, that is again converted into mass concentration. And in the sensor manufacturer, they kind of train the data with a certain environment, like a cigarette smoke with some reference instrument. So that really characterizes the sensor. So each different sensor has different characterization there. Okay, let's move on to this chart. This is a chart of the proprietary data. And y-axis is proprietary data, and x-axis is a reference data. And then, like Brandon covered before, the proprietary like to overestimate about 1.6x against the BAM. And then let me just introduce two models we developed. We have a physical model, which is a gray one, and a multilinear model. These are the physical model. First is using a particle count getting from the proprietary, and then we estimate some size distribution and density to convert into mass concentration. And then multilinear model is adding some more variables like a ratio of count, temperature, or humidity to reduce the error a little bit. But anyway, these are pretty close. These are physical model and the multilinear model are pretty close, but with using these approach, we can really put them into one-to-one line. The good thing about here is if you look at the left-hand side chart, this is at a log scale, but it's unadjusted to physical model. But they land onto the one-to-one line. That way, we really can reduce the misclassification of AQI, like green is always green, yellow is always yellow, and then red always red. So this is a good example of our analysis and then the algorithm. And here's another local sensor application. This is what happened in the campfire the last year, November time, I guess. And then it kind of started with, that time we had board meeting, and then the board chair mentioned, I have to think about cancel the board meeting if the quality is over the standard. But we didn't have data. Okay, so we have first started thinking about, why don't we just install some EBAM or EFEM instrument because it has good quality of data because we are ARB. But thing is, that comes with pump, which is noisy and bulky, so we don't have that in your cube right next to you in the meeting room. So we decided go with purple air. And these are photos how they install, like this one and this one. So we know we developed that algorithm we talked about in the previous slide. With that, we use a linear model adjustment to improve the PM measurement, and here's the result. There's a time series data with PM 2.5, and then purple one and is purple air with a linear model adjusted, and then black one is outdoor band reference. It really tracks well, and then this orange one is an indoor purple air. So that way we really can measure good indoor purple air. This demonstrates the advantage of the algorithm as well as the sensor, local sensor. It's small and low power and quiet. And let's move on to another example. Let's widen the scope to the indoor to a bit bigger scale. Smoke monitoring program deploying the FEM instrument over the California. The regulatory sites are very average. That provide hourly averages. But now AB 617 kicked in, so we expect a community level air monitoring. So with that, we provided about 400 purple airs to Air District, and then we have the data and having minute to minute, and then the good time and temporal resolution data. Also, we are working on the satellite project, but it really has to have some modeling work, but hopefully can provide a bit wider scope. Again, here is how we are working on how we leverage the sensor usage. So let's move on. So far, I talked about some applications, and now move on to some current and future work a bit. So let me just start with sensor performance evaluation in field and chamber, and then the network adjustment and some visualization. So for field sensor evaluation, like I talked about the algorithm to develop adjust the appropriate data. But thing is, that model is trained with a certain environment, which is a fire, natural fire, wood fire in the Sacramento Valley region. The question is, can I use that for everywhere? And then we also know local sensor by and large overestimate PM when RH is high, and it is uncertain about the particulate size distribution impact, the speciation impact. So to characterize environmental impact sensor performance, we pick up 12 sites to represent various environments and range of conditions, like regional groups, temperature, wind speed. For example, regional groups say coast has kind of always high humidity, Sierra or mountain area for the summertime fire, and the winter low temperature. And further detail analysis, we need to well-controlled environment. So as we cannot control the real-world environment. So we have a chamber here. It's not running yet, but we have these many instruments, and then we can use that to validate the model we created. Also, we can check the range. We can also, another task we are looking at is explore the sensor degradation, which can be done by having a real controlled environment. So how sensors degrade over time. Now move on to network quality. Now, sensor allowed to have a better spatial resolution, but again, sensor is a bit less reliable than regulatory station. So this leads to a question like how to adjust or how to tell when the sensor goes bad. And the evaluate different network calibration methods is something we are working on. Let's just give some ideas, like there are some 3 ideas here: co-location and dispatch, co-locate sensor, and then dispatch those sensors, or co-locate in one place and then propagate the parameter to adjust to different sensors already dispatched, already deployed, or we could have a mobile station with a little bit better grade, reference grade instrument to move it around to adjust or calibrate the sensors. Okay, again, the sensor really can provide a high resolution temporal and spatial data. That means we receive a lot of data to analyze, well, a lot of data to manage. So a visualization tool like dashboard like this one will help doing such work. So here's actually internal dashboard data tool, an internal dashboard. Let me just quickly go through it. Like top part, just tell where are the local sensors, and then where is the regulatory monitoring station, and then lower left just have some time series data with different stations. And then lower right has some heat map to tell some pattern hour of day or day of the week. And with that, we can visualize lots of data, and also the evaluate agreement with regulatory monitors because we have all the data in place. And then that really helped to explore the calibration methods. Okay, here's a summary. I talked about the evaluation field and chamber evaluation that help understand environmental impacts on sensor performance and product life. Also, I talked about the sensor network can enhance the spatial and temporal coverage, but once QA/QC'd, and analytical tools must keep up with new technology like the dashboard I mentioned. And the last, understanding performance improves messaging. And let me just take you one last slide of messaging. I find it interesting, but the left-hand chart, this one is a screenshot of PM data. And then my personal impression here is this, it's a Shasta County, I guess. Entire Shasta County is really bad air quality. Like this is very unhealthy. But when I look at the regulatory monitoring data, I don't see the sign at all here. So I dive into the data here, then it turns out there's one faulty sensor providing a high value data, and I don't see the other sensors providing that high value. So lesson here is, well, message here is, so sensor data are not regulatory data, and they're not treated as regulatory data. And another message is understanding sensor performance and appropriate visualization really improves the messaging. So that's my presentation. Thank you very much.
Okay, any questions for Koki or Brandon?
Let's see, for Brandon, your 12 sensors paper, is that based on new studies, or are you using the same collected data you've gotten over the last couple of years?
That's using the data from the AQ-Spec evaluations, so there are different time periods throughout a 3-year period.
And for Koki, can you share your algorithm that you're using for correction? Is that, I know you with qualifications.
That's possible, and then the idea is that, but let me just tell a little bit more about that. Using the Propoyer, because I'm using Propoyer at that time, the Propoyer provides 4 bins of particle count, I think 4 bins of particle count. Using that particle count and then give some density and to pretty much come up with that, mass concentration. And then sharing the algorithm is no problem. But again, we train that data set in the Sacramento Valley data.
So this is a really broad question, multifaceted, so I apologize for both of you. What we're starting to see with the AB617 community and a lot more people doing community monitoring on their own is sensors, low-cost sensors that will give you instantaneous data on the instrument and not have data logging capabilities. Have you experienced trying to test any of these and forcing the instrument to data log, or is that something that you're going to be getting into as well for some of these low-cost sensors that just give, instantaneous data? And then I guess follow-up is, if you do, how far, if we were to test one of those, our staff, we're thinking about actually just pinning into the boards itself, cracking it open, and then at that point, how far do you go down that before we just recreated a whole new sensor that's not valid to what is actually being developed?
Yeah, good question. So for the AQ-Spec side of things and evaluating sensors, we've spent hours and hours trying to get data out of some of these sensors. And some of them, they're just equipped where they send data to a cell phone app and there's no portal to actually obtain that data. And part of that may be design limitation. Some of it may be on purpose. They don't want that data actually being out and people using it. They just want to see that real-time visualization. But that's one of the requirements. And so to start off an AQ-Spec evaluation, we do a bench test. And the core function of that bench test is, can we obtain data and can this device be deployed in the field for 2 months? So there's a handful of sensors that have not passed the bench test. And we've got 3 or 4 on our plate right now that we're trying to work through to get to pass the bench test to even get under AQ-Spec evaluations.
Once a sensor passes the bench test, how long does it take from start to the final report? How much effort does it take on average to evaluate one sensor?
Yeah, so it takes 2 months in the field. Usually we'll get it deployed a couple weeks, maybe a week or 2 after the bench test. Then you have your 2-month field evaluation, and then we compile the data, time match it, and then develop the actual report. And that's usually within about 3 to 4 weeks post the 2-month field evaluation. So total time range would be 3 to 4 months for a field evaluation to come up online. And then after that, the laboratory evaluations are scheduled out. And we also have the testing protocols we're developing for the ASTM and for the VOC. So it's not sequentially time-wise. I can't give an estimate for that because it depends on the projects. Several other projects are using that chamber currently.
So you guys use the BAM as the reference instrument to test all the sensors. I'm wondering if you have any thoughts on understanding bias associated with the measurement principle. The BAM is a much different principle than, say, the purple air, which is the optical measurement. Even the BAM doesn't even provide a full hour of measurement. So I was just curious if you guys have looked at teasing out differences in that bias that may be caused purely to differences in the measurement principle.
Yeah, that's a great question. So AQ-Spec evaluations happen at our Rubidoux air monitoring site. At that site, we have the BAM, which provides us a 1-hour data point. And so all of the data I showed was 1-hour data points. The sensors were averaged up to 1 hour. If you look at the AQ-Spec evaluations, you will find about the 3rd slide on each evaluation will be a BAM-GRIM comparison. And then we'll also go through all of the evaluations will be done typically for 5 minutes, 1 hour, and 24 hours for PM2.5. So you can find that. There are times where the sensors will correlate better with the GRIM because it has that optical measurement. It's also taking measurements every 60 seconds, similar to what it is doing with the sensors. The reason I chose that was because we have really good consistency, which are BANS measurements for all 3 years. I don't have that with the GRIM. So there's some significant downtime for the GRIM, and so I would have knocked out probably 3 or 4 of the sensors just based on data recovery of the GRIM.
Yeah, we also aware of the difference. We use a T640, but it's also using optical, and then it's a bit easier than comparing those OPC sensor with T640 because they're pretty similar. But again, we found a little bit delta in T640 and BAM, so that's another thing we are working on. But because these are T640, those optical sensors are pretty similar, so we are starting with comparing this and then move on to compare with BAM. So that's kind of an idea.
I had a question on concerning, I'm over here on this side, concerning how it was determined at the time length, I think you said 2 months, for analysis instead of maybe 1 full year to go through all of the seasons to be able to see if a seasonal change is impacting them.
Yeah, that's a good question, and I think that's kind of the scope of the program. We're a sensor performance evaluation center, not a certification center. So I think as things transition in the coming years from an evaluation center potentially going to that kind of standards, and it'll definitely have to take into seasonality. And that's one of the reasons why I filtered all the results at the 50 micrograms per cubic meter, was to try and even out that seasonality difference between the evaluations that are taken part different times of the season. The 2 months is a good time frame. It gives you a long enough time frame to get a good range of PM2.5 values and typically a range on temperature RH conditions. So I didn't show it, but I do have a table of all of the temperature and RH conditions. We do see seasonal differences at that locations in temperature, not so much in RH. Over a 2-month period, we get a good range of RH values, and they're usually typically pretty close. It's a more of a dry, arid environment, I guess, inland site. And PM2.5 is pretty standard. I mean, it's typically 12 to 14 micrograms per cubic meter, plus or minus 10 or 12 on average at that location.
Hey.
Yeah, that's a good point as well, Mike. That's why we have the laboratory coupled with it, is so we can then get the full range of PM2.5 concentrations or gas concentrations that we might not see in the field, and as well get a range for temperature and humidity that may not be present in the field evaluation.
Hey, Koki, what is the dream scenario for adjusting all purple air data in California? Would it be size distribution analyses by region, and then also composition to estimate density, and then have that vary by season? What would be like, I guess, the dream?
Well, I think our first priority is come up with best practice. So dream would be if the sensor can really useful at given environment. So some sensors, here's my thought. Some sensors really R-square is not bad, but if you focus on some area, which is then maybe that sensor may be good. So then we can just kind of share our idea, like, okay, use this when this environment, you can rely on that. But kind of that way, I want to be a little bit more flexible in providing information for users. Yeah.
Sorry, one more from me. I'm not sure about with Koki, but I know AQ-Spec, we do you guys do the two-month outdoor, and then you go to laboratory if it passes the muster on that one. Have either of you explored or have started testing longevity of any of these small air sensors, like cradle-to-grave testing or anything, to show possible sensor degradation, loading of those optical sensors, etc.?
For the lifetime testing, we're expecting a chamber to come when it gets ready. I just like to using that with a control environment to see how we have some data seeing, I don't have an exact number, but seeing sensors getting a little bit less sensitive when getting old, but we just want to quantify it, but we are waiting for really chamber to do that work.
We're doing some of that in the protocol development for the ASTM indoor air quality testing protocol. doing like a longevity test. Yeah, it'd be for indoor sensors, PM 2.5, and I think carbon dioxide.
Okay, any more questions? If not, we have a break until 3:30 when the breakout sessions will start again. Just as a reminder, we have vendors over in Ballroom C here, and CARB's audit van is also out the back doors of Ballroom C. Thanks again for filling out your evaluation cards. You can just leave those on the chairs and I'll pick them up. Thank you.
Tough to see what the screen is.
I kind of forgot that. Yeah. Then you're kind of standing there.